Hey everyone, welcome back to Power Electronics. I'm Tim, and today I want to do a bit more about DC modeling, right? DC modeling. And the converter I wanted to look at was the Cuk converter. And specifically I wanted to look at this. It's featured in Fundamentals of Power Electronics, right? It's actually, the problem is a little bit more complex than other problems because it involves a little trick that is kind of hard to deal with, and I wanted to talk about that. So what is the Cuk converter? Well, the Cuk converter, invented by Professor Cuk, looks like this. So we have an inductor connected to the input, followed by a capacitor. We have two switches, a MOSFET and a diode, right? One controlled switch, one uncontrolled switch, followed by another inductor, which is then connected to the output. This is the Cuk converter. And before we actually, do the DC modeling, I wanted to note a few things. So one, this is an inverting converter. That means V out is negative with respect to the input, right? And I want to kind of clear that up in the beginning because I'm going to define my output voltage in this way, right? And there's another kind of interesting way of thinking about this, right? And that's basically the direction of this diode. And now the direction of the diode, actually, you kind of have to know that what the direction of the current and voltage are going to be. But the fact that it's drawn like this indicates that the current is going to flow in this direction through the diode, right? We're going to have current flowing downwards, right? And if you think about this loop, that then means that the current is going to flow, the average inductor current, at least, is going to flow to this terminal of the load resistor, which means that the output voltage is going to have this configuration, if the input voltage is positive. Cool. So let's get to labeling, right? So we have L1, C1, L2, and C2, right? Pretty normal so far. And let's label some voltages and currents. So we have VL1 in that direction, VC1 in that direction, and again, we're using passive sign convention, so we can, once we define the voltage, we can define which direction the current should go, right? So it should go into the positive terminal for passive components, right? So we have IC1, IL1, we've defined the current going through IL2 is in this direction, or we've noted that it should go in that direction if the output voltage is negative, which means that the voltage should be in this direction. And we can define the capacitor current to flow in this direction, right? So this is IC2, we can say, and the output voltage, which happens to be equal to the capacitor voltage, is defined like this. Great. So we're going to do DC modeling. Conventional DC modeling without losses isn't very complicated. However, when we introduce losses, it becomes more complicated. So let's talk about the losses we're going to introduce. Only conduction losses, right? So we have L1 is going to have a resistance RL1. L2 is going to have resistance RL2. Q, our switch, Q and D. Q, the MOSFET, is going to have an on resistance, R on. And the diode D is going to have a forward voltage drop. These are the only losses we're going to consider. And really, we're going to note that this is kind of the challenging loss to deal with. And we'll see why it's challenging when we get to this. So, this is kind of all the information we need for now. So, let's get to it. So what do we do? Well, again, if we're trying to construct a DC model, what we do is we draw the converter in both switching states, write the IVSB, CCB, and input equations, and then from those equations, we construct circuits, which we then combine together using DC transformers to construct our DC model. So let's do it. From 0 to DTS, the first switching state. Well, Q is on, D is off, right? So we know, and we're going to include the losses in these sketches, right? So we have the input voltage, the inductor has a resistance RL1, the MOSFET is on. It has an on resistance, R on, right? So we'll draw that here, R on. This is RL1, this is L1. This is connected to a capacitor, C1, right? The diode is off, I won't draw it. This is then connected to an inductor, L2, which has an on resistance, RL2. And this is then connected to the output capacitor and the load resistor, right? So this thing I'm going to call R load. So we have R load, and again, the voltage, the output voltage is defined in this way. Cool, so that's one side, right? And the other side, or the other half of the converter, you could say, occurs between DTS and the end of the switching cycle, right? And here the diode is on, and the MOSFET is off. So we have the input voltage, the inductor resistance. The MOSFET is off. This is connected to a capacitor. The diode is on, right? And the forward voltage drop VF is in this direction, right? So this is C1, RL1, L1. This is connected to an inductor, L2, which has a resistance RL2, which is then connected to the output capacitor, and the load resistance. And this is again V out. Great. So what do? We do IVSB and CCB. So we have two inductors, two capacitors. That means we're going to have two IVSB equations, two CCB equations, and the input equation. So let's get to it. IVSB for VL1 tells us that the average voltage applied to the inductor over one switching cycle is equal to 0. If we do it in this fast way that we've been doing it in the past, we look at the first switching state and consider the voltage across this device, VL1, right? And note, IL1 flows in this loop, right? And we've defined IL2 and we've defined IL2 to flow in this direction, right? And we can do the same thing for here, IL1 and IL2, right? And this is going to be important to know because these currents are going to flow through the resistors and cause voltage drops. So in the first switching cycle, right, we choose a direction, and whenever voltages line up with the direction we're going, it's positive. When they are anti-parallel to the direction we're moving in our loop, then it's negative, right? So the voltage across VL1 is equal to VG. We have a voltage that is anti-parallel to our loop, so we subtract IL1 times RL1. Again, we have a voltage across this resistor R1, which is anti-parallel to our loop, and it actually has two currents flowing through it, right? It has IL1 and IL2. So we subtract off IL1 plus IL2 times R1, right? And that's the voltage, right? We just consider this loop. In the second switching state, D prime, again, we consider this loop. So we're looking at the voltage across VL1. So again, we have VG, right? And again, we have IL1 flowing through RL1, anti-parallel to the direction of our loop, right? So it's IL1 times RL1. We have a voltage VC1, anti-parallel to the loop. And I'm doing SRA here pretty liberally because we're just doing a DC model. We're not really interested in ripple per se. And then finally we have minus VF. Cool. So again, that is this loop. And that is equal to 0. So let's do some simplification first. One thing we can note is that in both switching states we see VG and IL1 times RL1, right? VG and IL1 times RL1. Because D plus D prime is equal to 1, we can combine these two into VG minus IL1 times RL1. What else do we have? Well, we have this really interesting component, right? This actually contains current from both loops, right? So this component of the equation actually couples the loop IL1 to IL2 in a way, right? Because this loop is supposed to represent IL1, but somehow IL2 shows up. So we're going to figure out how to deal with it. For now, what I'm going to do is I'm just going to leave it as IL1 plus IL2, right? And then I'm going to group this D with the R on, right? So this D times R on is like the effective resistance. If we increase the length of time that the MOSFET is on, then we're effectively increasing its resistance. If we decrease the time, we effectively decrease the resistance. So this is, in a sense, an effective resistance that is modulated by the pulse width. So that's one term. The next term, right, from over here, we have minus D prime VC1, and then also minus D prime VF. And that's equal to 0. And this will be our equation 1, right? And that's going to form a loop. So the next thing we do is IVSB for VL2. And again, it says that the average voltage applied to the inductor over one switching cycle is equal to 0. Doing it in this simplified way, we think about the voltage across this inductor, right? And again, I've defined it in this direction, VL2, because we know that the current is going to flow in the direction I've indicated, right? Anti-clockwise. So, how do we do it? Well, we move around our loop, and voltages which align with our loop are positive, and voltages which don't align or are anti-parallel with our loop are negative, right? So I'm going to move in this direction, right? So let's start with this capacitor voltage, right? This aligns with our loop, so we have D VC1. Right, so we have D VC1. We have the voltage across R on. Again, it's the same voltage, right? It is this component, right? The IL1 plus IL2 times R on. It is anti-parallel to our loop direction, so we subtract it. And continuing on, we have V out, which is anti-parallel to our loop direction, right? You could say the arrow is going into the positive sign, so we subtract it, minus V out. And then again, we have the voltage across this resistor, minus IL2 times RL2. And that's it. We've done everything, right? This is kind of what we're solving for. Cool. So the second half, the second portion of the switching cycle, what do we have? Well, again, we can follow our loop. So voltages which align are positive, voltages which are anti-parallel are negative. So first, we have minus VF, right? Starting here, we have minus VF. Moving along, we have minus V out, right? Goes into the positive sign. And again, we have minus IL2 times RL2. And that's everything, right? Those are the components that we have to worry about. So let's simplify this. So again, we can note in these two components, these two halves of the switching cycle, we see IL2 times RL2, right, in both of them, and we also see V out in both of them. So because D plus D prime is equal to 1, we can simply, pull them out as IL1 times, or IL2 times RL2 and V out. What else do we have? In this first switching cycle, we have D VC1, or first switching state. We also have minus, again, I'm going to leave this as IL1 plus IL2 times DR on. And the final component we have is minus D prime VF, right? And that is equal to 0. This is our equation 2, right? So we're going to make a loop out of this, eventually. Great. Now what do we do? Well, we think about IVSB, or CCB, on capacitor C1. It says the average current applied to a capacitor over a switching cycle is equal to 0. Doing it in our simple way, what do we have? Well, in the first switching state, this is the direction of IC1 from passive sign convention. In the first switching state, IC1 is equal to minus IL2. And in the second switching state, IC1 is equal to IL1, right? So it's a pretty simple equation, right? So in the first switching state, D prime, it's minus IL2. And in the second switching state, it is IL1. And that's equal to 0. So what this is saying, right, is that DIL2 is equal to D prime IL1. Great. This is equation 3. And then we're also going to think about the output capacitor. And again, this is similarly kind of easy. So the average current applied to the output capacitor over one switching cycle is equal to 0. Now note, in both switching states, so first of all, we've defined the current IC2 to be in this direction, right, because of the direction of the output voltage, so we're defining the current in this way. In the first switching cycle, it's equal to IL1 minus V out over R load, and in the second switching cycle, it's equal to IL2 minus V out over R load. In both switching states, because the inductor is directly connected to the output capacitor, what it's saying is that the average inductor current is equal to the average output current. So I'll just write it out here. Again, this is like the simplified way of thinking about it. So we have IL2 minus V out over R load in the first switching state. And in the second switching state, again, we have IL2 minus V out over R load. And we know from CCB, steady state, this should be equal to 0. And again, we see in both switching states, the same component, D plus D prime is equal to 1. That means that it's saying that IL2 is equal to V out over R load. This is equation 4. And we have one more equation, and that's the input equation, right? Basically it's saying, what is the average input current? And we can write this equation in this way. And really, very straightforward. In the first switching state, if we look back to our circuit, the first inductor, L1, is directly connected to the input. So in both switching states, the current coming out of the input source is equal to the inductor current. So in state 1, Ig is equal to IL1. In state 2, Ig is equal to IL1. Right? So basically all it's saying is that the input current is equal to the inductor current. So we have D times IL1 plus D prime times IL1 is equal to Ig. In other words, the input current is the inductor current. This makes, the input and output equations kind of simple. So, what do we do now? Well, we have 4 equations that we've simplified. Now, we construct the equivalent circuits from them. Right? So each of these loops can represent a KVL equation or a KCL equation, right? So this first equation, equation 1, represents the inductor current loop. So what we can do is imagine that for equation 1, we have an imaginary inductor, right? An imaginary inductor L1. I say it's imaginary because this whole idea of DC modeling is basically to eliminate the inductor, right? Or eliminate the dynamics of the inductor. We're just looking at the DC components. So it's there. I'm drawing it there because this is what this loop represents. We can imagine that this loop carries the inductor current IL1, right? But its effect isn't really there, right? We're just looking at the DC components. So what's going on in this loop? Well, so again, we're looking at equation 1. Maybe I'll do it in red, right? We're looking at equation 1. So what do we have? We have Vg minus IL1 times RL1. So one thing I want to note is that for this loop, because this thing is representing IL1, everything else is either a dependent source or loss. The only real variable, the only independent variable is the inductor current. And that isn't even really shown as a component. It's just assumed to be flowing in this loop. So we have Vg, a dependent current, voltage source, Vg. Then we have IL1 times RL1. So this basically, IL1 flows through this loop, so we have a resistor RL1. Then we have this dr on, right, which is kind of interesting, and it's multiplied by IL1 plus IL2. So somehow R on is shared between the two loops, and that kind of makes sense, right? If we go back in this loop, R on is shared between the two loops, right? R on is shared between the IL1 loop and the IL2 loop. So it kind of makes sense. And this is the trick, that R on is really coupling loop 1, equation 1, to equation 2. So that's how we should construct these loops, right? These aren't independent loops. They're dependent on each other through this resistance R on. Right? So we're going to have a resistor R on, dr on, right? The effective resistance. And then we have a dependent voltage source, D prime VC1. And then this loss, right, which ends up being an independent voltage source, D prime VF. right? So this isn't providing any power, it is consuming power. So what do we have? We have our dependent voltage source, VG, right? Then we have our imaginary inductor, which has some resistance, RL1. We have an independent voltage source, which is a loss. This represents a loss, which is D prime VF. We have a dependent voltage source, which is D prime VC1, right? Minus D, right? If we could consider this loop, we subtract off D prime VC1. And then we also have our final resistor. And I'm going to draw it like this for now because this is like an incomplete loop, right? So this is DR on, right? So again, IL1 flows through this loop. So we can imagine IL1 is over here. And it means, the way I'm drawing it, the reason I'm drawing it like this is because I'm going to imagine that IL2 flows over here, right? So we're going to connect the loop from equation 2 to this resistor, right? So I'm leaving it open for now. Right, and I'm actually going to skip equation 2. I'm going to go and think about how this D prime VC1 couples to something else, right? So to do that, we have to look at equation 3, right, over here, right? So in this first equation, we have D prime VC1, and that is going to connect to this D prime IL1, right? So I'm going to switch over to equation 3. I'm going to consider equation 3, right? And equation 3 says that, so again, this represents our capacitor C1, right? And we're dumping in D prime IL1, and we're taking out DIL2, right? So this capacitor is also coupling the currents IL1 to IL2, right? This C1 somehow relates IL1 to IL2, just as this resistor also does that, right? So again, this is a pretty simple equation. D prime IL1 is equal to DIL2. Let's just make sure that I got that correct, right? D prime IL1 is equal to DIL2. Perfect. Okay. So then this loop then couples back to equation 2. So let's do equation 2 now. So we have to think about equation 2 a little bit specifically, right? Because we've already defined this voltage, right? We've defined the voltage across this resistor to be in this direction. If we're going to hook this up to another loop, then we have to pay attention to the fact that this is already defined. The direction of this voltage is already defined, right? So looking back at equation 2, we see that dVC1 has the opposite sign to IL1 plus IL2 times DR on, right? So that means that when we put this voltage into this loop, it has to point in the opposite direction of this voltage, right? So going back down here, if the voltage across this resistor points in this direction, then that means that the voltage provided by this dependent source should point in this direction, right? So this is dVC1. Again, you just have to be careful when you're putting that together. So we can again imagine this resistor or this inductor L2, and again we can imagine the current IL2 flows in this through this loop, right? So this has some resistance RL2, right? We have minus D prime VF. So it should point in this direction, minus D prime VF. And then finally we have minus V out. Right, so that exists over here. Cool, so we've connected these loops together. So this is V out. Great. So we're kind of almost there. We just have to model the input and the output now. So the output is pretty simple, right? The output is just saying that IL2 is equal to V out over our load, our load is included in this equation. So we can couple it to the output in this way. We have IL2. IL2 flows in this loop. It also flows in this loop. Is equal to V out over our load. And I'll just define V out in this direction. Again, we could flip it around, but this is really just going to be a transformer. The direction is really up to you. The other thing we have to include is the input, right? So we also have an input equation, right? And the input equation just says that VG, the input current, IG, is equal to IL2. That's it, right? This is equation 5, right? So, sorry, this should be IL1. So we can totally transform this into a transformer. We can turn this into a DC transformer, but really, it's just a one-to-one transformer where the dots are lined up, right? We have IL1 flowing here, we have IL1 flowing here, we have VG over here, we have VG over here. So that means that really this is just a one-to-one transformer that does not invert anything, right? So it's a DC transformer, the dots are in the direction you expect. One-to-one, perfect. So that is what the full model would be. I'm going to ignore it for now because we already have the same voltage here, right? Bringing this over the transformer doesn't do anything at all, right? It just kind of makes it would turn this dependent source into an independent source. Similarly, over here, in a similar way, this is also a one-to-one transformer, right? Except the dots are inverted, right? Because the voltage is flipped, right? So we can, and this is really just because of the way I've drawn it. So we could turn this into a one-to-one DC transformer. Again, same kind of thing. I'm going to ignore it because the voltage is already here, but this equation is important. So we'll think about the equation. We're going to ignore the part of the loop. So really what we're interested in is this stuff. How do we convert this into something that makes sense? Well, this is the most complex part, right? We have basically, this is going to be a transformer, and this is also going to be a transformer. But I'm going to take a shortcut, right? And the reason I'm going to take a shortcut is because it's going to make it look a lot easier when we fully simplify it, right? So we have d prime VC1 over here, and we have d VC1 over here flipped. That relationship of voltages already looks like a transformer. So what I'm going to do is I'm going to simplify, I'm going to bring these two voltage sources together into a single transformer, right? Noting that the relation, well, first of all, the voltages are flipped, so we know that the dots should be on opposite sides. And we know that V1 over V2 is equal to N1 over N2. V1, what is it? Turns out it's d prime VC1. V2 is d VC1. Right? If we cancel this out, it tells us that N1 is d prime and N2 is d, right? And you might be thinking, shouldn't there be a negative sign? Well, I've accounted for the negative sign by flipping the dots. So this whole complex equation thing, right, simplifies into a single transformer. So I'm going to redraw this this whole loop, right? And I'm going to consider the input voltage to be already transferred through a transformer. So we're going to have VG, which then connects to a resistor, RL1. All right, RL1, we have d prime VF. And this is connected to a transformer, right? Whose bottom terminals are connected together, right? So we have this transformer, a DC transformer, inverted dots with a turns ratio of d prime to d. Right? At the bottom of this transformer, we have a resistor, dR on, which then hooks up to the second loop, right? The IL2 loop, which has a resistor RL2, a forward voltage drop d prime VF, and the output voltage. So we have RL2, d prime VF, and the output voltage. So I'm just going to include it as a dependent voltage source. I'm not going to include it as a voltage source. It doesn't really make sense. It's a load, right? It should be a resistor if it's anything, and we can consider it as a resistor, but I'll just draw it like this. This is V out, this is d prime VF. And again, we have IL1 flowing in this loop, and we have IL2 flowing in this loop. All right, so this is the final loop, right? This is the final thing that we use to solve this equation. Now the tricky bit is actually solving it. So we're going to use a few tools, right? Namely, we're going to use this transformer. This transformer is really the thing we need to solve this in an easy way. So what does the transformer say? Well, it basically says what the CCB equation says, right? CCB for cap C1. It says that, well, it says IL1 over IL2, or I1 over I2, is equal to N2 over N1. In this case, that is equal to D over D prime, right? And that is exactly what CCB says. So I'll just rewrite it in a slightly different way. It says IL1 is equal to D over D prime IL2, right? And again, this is from CCB. We also know that IL2 is equal to V out over R load. So this is helpful because now every time we see IL, either IL, we can relate that back to the output voltage, right? We can relate it back to V out over R load. And that's going to make the equations a little bit simpler. This is going to allow us to eliminate those variables from our equation. The second thing I want to do is note the other half of the transformer equation, right? The other half of the transformer equation is that V1 over V2 is equal to N1 over N2, which is D prime over D, right? And I've defined the voltages in this way, V1 over V2. In other words, what this is saying is that dV1 is equal to D prime V2. Okay, that doesn't seem to be very helpful, but yeah, like it should do something, right? It does, right? This actually is how we're going to solve it. We're going to find an equation for V1 and find an equation for V2. Okay, so let's do it. How do we do this? Well, V1 is equal to VG minus IL1 times RL1 minus D prime VF minus IL1 plus IL2 times dr on, right? That is what V1 is equal to. Now V2. Note, we have to be careful about the direction that we're considering, right? So we can go in this direction, but that would actually give us minus V2, right? Because we're kind of considering, we're going into the minus sign of this, of the way we've defined the voltage. So we just have to note, we have to ensure to include a minus sign. So what do we have? Going in this direction, we can do that. We have minus IL1 plus IL2 times dr on minus V out minus D prime VF minus IL2 times RL2. Cool. So we're almost there. Basically, now we just replace all the ILs with something related to V out, and then we equate the voltages. So let's do that. So V1 is equal to VG minus, well, what is IL1? IL1 is actually D over D prime IL2. What is IL2? It's V out over R load. So I'm just going to write it in this way. RL1 over R load times V out. Cool. Minus D prime VF. Minus IL1 is D over D prime IL2. D over D prime plus 1 is equal to 1 over D prime. Right? So this whole thing is actually equal to D over D prime R on over R load times V out. Right, you can check that for yourselves. Now let's do minus V2. So remember to include this minus sign just because of the way we've defined the voltages. So what do we have? Again, this exact same equation, right? So we have minus D over D prime R on over R load times V out minus V out minus D prime VF, and then this IL2 minus V out RL2 over R load. Cool. One more step, right? So now all we have to do is D times V1 is equal to D prime times V2. So we have what V2 is, right? We can actually just cancel out all these minus signs, and we're good. So D times VG minus D over D prime RL1 over R load, V out, minus D prime VF, minus D over D prime R on over R load, times V out is equal to D prime times D over D prime R on over R load plus V out plus D prime VF plus V out RL2 over R load. Cool. So what I'm going to do is I'm going to bring all the V outs to this side, and then all the VG and VF stuff to this side, right? So this is like V out, and this is like VG. So let's do that. So we have minus D over D prime RL1 over R load times V out minus D over D prime R on over R load times V out. All right, that accounts for this and this. Sorry, times D. We have to include the D. So D, right? There's a D squared now. Minus D prime times DR on over R load times V out. So minus D R on over R load times V out minus D prime V out minus RL2 over R load times V out, right? That's one side, and on the other side, we're going to have minus DVG plus D prime VF plus D prime squared VF. All right, almost there. Now we just have to factor, right? So I'm going to, there's a bunch of extra minus signs, so let's just get rid of all those minus signs. Minus, 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 minus. This becomes a minus sign, this becomes a minus sign. So we're going to factor out V out. Actually, what I'm going to do is factor out D prime V out from everything over here. So what are we going to get? We're going to get D over D prime all squared RL1 over R load plus D over D prime all squared R on over R load plus D over D prime R on over R load plus 1, right? Plus RL2 over D prime R load sorry, there should have been a D prime over here. So I factored that out. Plus RL2 over R load. And that is equal to, well, I'm going to factor out DVG from everything over here. So we have VG 1 minus, so we're going to factor out a D. That's D prime VF over VG minus D prime squared over D VF over VG. Right, and now we kind of have to simplify. So we can group these two things together. So D over D prime, we can factor out D over D prime from both terms. So we get D over D prime plus 1. This is equal to 1 over D prime, right? And we can also factor out D prime VF over VG. Right? This thing is actually a very similar term to this. This is 1 over D. So let's get there. So simplifying again, we have D prime V out times D over D prime all squared RL1 over R load plus RL2 over R load plus, this is 1 over D prime, D over D prime squared R on over R load plus 1 is equal to DVG 1 minus D prime over D VF over VG. Almost there. Now we just have to divide it all out, right? So what are we looking for? We're looking for M of D, VG of RL1, RL2, R on, VF, all this stuff. This is what we're looking for. And this is a ratio of the output voltage to the input voltage, right? So I'm going to divide this side by VG. I'm going to divide this side by d prime and all this stuff. So let's do it. V out over VG is equal to d over d prime times 1 minus d prime over d VF over VG all over 1 plus RL2 over R load plus d over d prime all squared RL1 over R load plus d over d prime squared R on over R load. And that's it. This is the solution, right? And it kind of makes sense. It looks very similar to the form of like a regular converter. And that's what we expect, right? We don't expect some weird signs because it's inverting. We expect to see basically this represents a voltage divider. Actually, let's use a different color. Right, so this thing basically represents a voltage divider. Right, we can multiply the top and bottom by R load, and we get R load over R load plus RL2 plus blah, 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 blah. And this represents a voltage drop from the forward voltage drop of the diode. And then over here, this is the ideal conversion ratio. I'm used to writing inductor. This is the ideal conversion ratio. And you should note that there's no minus sign. There normally is a minus sign, but it's removed because of the way we've defined the output voltage, right? So way back up here, the very beginning, we define the output voltage to be negative, right? Because of that, the minus sign is basically accounted for in the way we've defined it, so it's just d over d prime. So we have the ideal conversion ratio, which then means that, let's use this color, which then means that this whole thing is related to the efficiency, right? This represents the conduction loss efficiency, you could say, right? It doesn't include switching loss or anything, it's just the conduction loss components. So this is the final solution, right? And it lines up with what we expect. Ideal conversion ratio times efficiency. Efficiency involves a voltage drop, and it also involves a voltage divider. And that's it. That's the final solution. So very complex converter, takes a lot of algebra to solve. You'll notice that a lot of DC modeling with losses takes a lot of algebra to solve. Figuring out this really important R-on coupling the two loops is really the trick to solving this converter, right? Solving this DC model overall. This is the trick, right? If you don't find this, then you're not going to get the right solution. That's what it's all about. And hopefully you enjoyed this, and I'll see you guys next time.